Let's discuss sampling distributions and the central limit theorem. Before we get there, let's talk about where we're going and where we headed, right? Where we've been and where we headed. Um, what we've been doing predominantly so far this semester is along the lines of like planning studies and then doing descriptive statistics. So whenever we talk about let's calculate certain statistics like the mean, the standard deviation, or um, the median, the quartiles, five number summary, let's make this graph. All of that stuff from the previous week, that was descriptive statistics, right? Where we're just talking about describing the results of the data we collected. Where we want to go is to inferential statistics. And some of you may have heard of things like hypothesis tests, confidence intervals, and things of that nature. Well, the hypothesis tests are in what we call inferential statistics. And that's where we're headed. But in order to get there, there's a missing piece that we're not going to spend a lot of time on, but it is probability, because probability is something that we need to make that transition from just talking about what happens in the sample to inferring to a population. And so, along those lines, this is what happens when we usually conduct statistical studies. We usually have a population in mind, and as you guys are well aware, population is the larger group who we're interested in drawing conclusions about. Again, we don't have access, we don't have the resources to collect data on in the entire population. So usually we collect a random sample. Hopefully we'll be able to collect a random sample from that population. And we will end up with the sample of size n. With that sample, we're going to measure the individuals in our sample on the variables that we're interested in, and then we're going to calculate the statistics, and that is the part where we call our descriptive statistics. We can also make graphs and charts and tables and things of that nature. Well, usually in research, we don't want to stop there. We want to draw conclusions back to our population. And that is the part which we're calling statistical inference. And that's the part where we need that probability theory to help us draw conclusions about that population. But before we get there, I want to ask a question about this process, right? We start with population, we do some random sampling, we get our sample of size n, and we calculate our statistic. For instance, we calculate the mean. Well, if we were going to take another random sample from the population, do you think we would obtain the same value of the statistic that we got in the previous sample? Or do you think we would get a different value of that statistic? Right? Well, if you think about it, since the sampling is random and the sample is a subset of the population, we're not going to get the same value, right? Because of the randomness, right? The people in that first sample are not going to be the same as the individuals in the second sample, right? And so when we have different people, our individuals in our study, in our samples, we're going to get different values on that variable, right? And so the answer to that question is no, and it's due to sampling variability. Well, if that is the case, right, how can we be confident in the results that we get when we conduct the study, right? If I'm going to get a different value, and if someone else does the same exact study and draw a sample from the same exact population, then they may get a different value of the statistic. How can I confidently draw conclusions about the population? What do I think that value of that summary statistic would be for my population? How can I be confident in that? And that's where probability and what we call the sampling distribution of a statistic comes into play. All right. And so a sampling distribution is a probability distribution. This is another term, right? We kind of hinted at this already. When we were looking at those frequency tables and like the histograms and things of that nature, those were frequency distributions based off of data we collected in our sample, right? Then we got to population distributions when we were talking about the density curves and the normal distribution. And now we're going to extend those density curves to what we call probability distributions. And that's what our sampling distribution is going to be. It's a probability distribution of a statistic that characterizes how the statistic varies across different samples from the same population. We know we have that scenario going on that when we take one sample, calculate our statistic, we're going to have a different value each time we do that. We need to be able to quantify how different those statistical values are going to be in order for us to confidently draw conclusions about that population. All right. So sampling distributions are actually calculated kind of in a hypothetical sense, or theoretical sense. They're calculated from repeated sampling from the same population. All right. And they basically are going to tell us how close our statistics would be to our parameter, which we're trying to draw conclusions about. All right. So let's talk about how we can actually construct this if we were going to do this in real life. And FYI, this is not done in real life. All right. So the sampling distribution, you can come up with the sampling distribution for any statistic. But what we're going to be interested in, since we're thinking about quantitative variables, is the sampling distribution of X bar, or the sampling distribution of the sample mean. Remember, we can use X bar to represent the sample mean. So in this scenario, it says a researcher is interested in the average amount of time high school students spend on homework each week, right? And so we have our population, which is high school students in South Carolina. Not going to be able to ask every high school student in South Carolina how much they spend on homework each week. And so we'll take a simple random sample of size N, ask those students how much time they spend on homework each week in general, and then we'll calculate a sample mean. All right. We'll put those students back into the population, take another simple random sample of size N, calculate the sample mean, and I'm going to get another value of X bar, which is the average number of hours spent each week on homework, averaged over all of those students in that sample. I can do that again. Take another simple random sample of size N, ask those students how much time they spent on homework, calculate the average of those values, and I'm going to get X bar sub 3. If I continue this process, I'm going to get a distribution of X bars. I'm going to have X bar 1, X bar sub 2, X bar sub 3, X bar sub 4. Each time I take that repeated sample, I'm going to get a bunch of X bars, right? These are the possible values of my sample statistic X bar. And that is how we create a sampling distribution. Now, instead of just listing those numbers of the average amount of time students spend on homework, what we can do is we can create a histogram, and there we go. We have the sampling distribution of X bar. All right. Theoretically, we want to do that an infinite number of times in order to see what all the possible values of our sample statistic would be. And then we would come up with the distribution, and that distribution together would be our sampling distribution of X bar. All right. Let's talk about some facts about that sampling distribution. All right. X bar is a random variable. That means before we even calculate or draw a sample, we don't know the value of X bar. In much the same way, if I were to go to one of those students, I wouldn't know how much they spent on homework before asking them how many hours you spend on homework each week, right? And so it is a random variable. So all of the stuff that applied to just regular variables actually apply to statistics. So I know that X bar is going to have a distribution, and I can calculate the mean of the X bars. It has special notation. The mean of the sampling distribution of X bar is sort of like a population type thing. So I'm going to be using mu. And anytime we're talking about a sampling distribution, as a subscript on that parameter, we put the statistic for which we're computing the sampling distribution for. So this is mu with a subscript of x bar. That represents the mean of the sampling distribution of x bar. It just so happens that specifically for the sample mean, the sampling distribution of the sample mean, the mean of that sampling distribution is the population mean of the variable x, okay, of the regular variable. So the mean is mu. So both of these have mu. I don't want this to be confusing, right? And so if I go back here, the researcher is interested in the average amount of time high school students spend on homework. If I go to each student x, the mean of that distribution would be mu, right? What I'm saying in that next slide is that the mean of the sampling distribution is also mu, all right? It's going to be the same value. The standard deviation of just the population of students, number of hours they spend on homework, that standard deviation is sigma. Well, the standard deviation of the sampling distribution of x bar is sigma with a subscript x bar. That notates that I'm talking about the standard deviation of the sampling distribution. It is the population standard deviation divided by square root of n, or the square root of the sample size. So I take the population standard deviation divided by the square root of n. That gives me my standard deviation of my sampling distribution of x bar. Now, these are a lot of terms here, and just to add to the number of terms, there's another term that we give this name. Instead of saying the standard deviation of the sampling distribution of x bar, we just say it's the standard error of the mean, or in short, the standard error. All right. So the standard error is equivalent to the standard deviation of the sampling distribution of the sample mean, and it is given by this formula here, sigma over the square root of n. The shape of the sampling distribution of x bar actually depends on the shape of the population distribution, so the regular population distribution, and the sample size that you take from those repeated samples. All right? Now, in certain cases, we know what the shape of that sampling distribution of x bar would be, and that is by way of the central limit theorem. The central limit theorem basically says that if the population itself is normally distributed, so my variable x, which may represent the number of hours spent on homework in a week, right? That may be normally distributed with a mean of mu and a standard deviation of sigma, right? So that's the population distribution, right? Stuff like the previous couple of videos. But if the population itself is normally distributed, then the sampling distribution of x bar is also approximately normally distributed, no matter the sample size. So if I take a sample size of 5 individuals, from a normal distribution, calculate my means, sample means repeatedly, that sampling distribution of the sample mean is going to be normally distributed. If the population itself is not normally distributed, I need a large sample size in order for my sampling distribution of my sample mean to be approximately normally distributed. All right? And large enough is greater than or equal to 30. So it says if n is greater than or equal to 30, then the sampling distribution of the sample mean is approximately normal, even if the population distribution of x itself is not normal. All right. Once that is the case, I can use those same formulas before, and I'll know the specific normal distribution so that I can do things with. All right. So 2 things with the central limit theorem. If the population distribution is normal, no matter the sample size of those repeated samples, your sampling distribution is also going to be normal. The second thing, if your sample size is large, I don't even care what your original variables population distribution looks like. Once the sample size gets to 30 or more, we can say by the central limit theorem that the sampling distribution is approximately normal. All right, this is a quick diagram. I have a population distribution of some variable that is bimodal, that is clearly not normal. But the central limit theorem says that as long as my sample size is large enough, then the sampling distribution of X bar is approximately normal. And I have a way to calculate proportions and probabilities so that I can say what's the probability of attaining a sample mean of certain values if I go out and do a study. So the importance of this, all of this sampling distribution of sample mean and the central limit theorem, it enables us to do statistical inference. That means we can conduct hypothesis tests and we can construct confidence intervals. In addition to that, one of the purposes of inferential statistics is that we can generalize our results from our sample to draw conclusions about the population. And then last but not least, as I was saying earlier at the end of that last slide, we can now calculate probabilities of obtaining certain values of our sample statistics. Let's look at a couple of examples. It says, suppose the amount of time South Carolina high school students spend doing homework in a typical week has a mean of 2.5 hours and a standard deviation of 1.2 hours. Random samples of 10 high school students are drawn from this population. What is the shape of the sampling distribution of the sample mean? All right, I just want to know the shape here. Well, it doesn't tell us the shape of the regular distribution. It just tells us that, okay, for this variable, amount of time spent on homework in a typical week, we know that it has a mean of 2.5 hours and a standard deviation of 1.2 hours in the population. But I don't know the shape of that distribution. And since we're taking samples of size 10, I can't use the central limit theorem to help me get the shape of that distribution. The central limit theorem only applies to n greater than or equal to 10. So it says, since we don't know the shape of the population distribution and the sample size is not large, we do not know the shape of the sampling distribution of the sample mean. All right. Now I did write this note here. It says if it was stated that the amount of time South Carolina high school students spend doing homework was normally distributed, then we would say that the shape is approximately normal because, hey, if the population distribution is normal, then no matter the sample size, even if it's less than 30, we're confident by this theorem that the sampling distribution of the sample mean would also be normal. Let's look at another example. So in this example, we have the same scenario. South Carolina high school students, the amount of time they spend doing homework in a week, mean 2.5 hours, standard deviation 1.2 hours. We're taking random samples of size 100. We want to find the mean, the standard error, and then describe the shape of the sampling distribution. Well, no matter the shape, the mean is always given by mu. And since I know the mean of the distribution of the regular variable, I also know the mean of the sampling distribution. It is going to be the same value, which is 2.5. So the mean of the sampling distribution of X bar is 2.5. The standard deviation we have to do a little bit of work with. The standard deviation is the population standard deviation, which is 1.2 hours, divided by the size of the sample. Now I've got to take that 1.2 and divide it by the square root of 100, and that'll be 0.10. I didn't type that in there, but 1.2 divided by the square root of 100 is 0.10. FYI, I do want you to know this. You can use JASP. So if you don't have a calculator and you want to do this calculation, you can use JASP. If I go to JASP here in the R console, so let's say I didn't have that up. I have my R console. If you ever lose this R console, remember you can always go to this plus sign here, scroll and click the check mark for R console. Um, but if I wanted to do 1.2 divided by the square root of 100, the square root function is sqrt, and then I will put the value that I'm taking the square root of in parentheses. So I'll do 1.2 divided by the square root of 100. I'll click run code, and of course we'll see that that's 0.10. That's 1.2 divided by 10. All right, wasn't necessarily to do that, but I did want to show you that. All right, so our standard deviation is that value. And then if I want the shape of that sampling distribution of your sample mean, I don't know the population distribution shape. I only am given the mean and standard deviation. However, my sample is of size 100. 100 is greater than 30. And so by the central limit theorem, I know that the shape of the sampling distribution of the sample mean is approximately normally distributed. And so everything that we've done with the normal distribution so far applies to this example. And I know how to draw my normal distribution. It's going to be centered at 2.5. And the distance between that line of symmetry to one of those inflection points would be 0.12. All right. And so now let's look at one last example here. I have the same scenario. We're taking random samples of size 100, but now I want to calculate a probability. It says, what is the probability that the researcher will attain a sample mean that's between 2.5 and 2.75? All right. Well, now that I know, based off of what we did in that previous slide, that the shape of our sampling distribution is approximately normal, and I know the mean of that and the standard deviation or the standard error, then what I know is that X bar is approximately normal, mean 2.5, standard deviation of 0.12. So I can go and I can draw a normal distribution. My mean or the center is going to be at 2.5, and I can get a graph that looks similar to this, right? I got my normal distribution. Now, what they asked me to do here is to find the probability that my sample mean is going to be between 2.5 and 2.75. All right. 2.5 is here, and 2.75 is here. I'm talking slow here because there is a slight error on this slide. I wonder if you can figure out what the error is on this slide. Note, I want you to note how I'm notating my axis here. I'm counting in standard deviation units, which I have done before, right? This is at 2.5. My standard deviation is 0.12, right? So if I add 0.12 here, I'll get to 0.62. If I add 0.12 there, I'll get to 0.74, so on and so forth. And if I do the subtraction, I'll get that, right? That is fine. That's not an error. I labeled this as the sampling distribution of the sample mean time spent on homework, right? That is fine. These values, 2.5 and 2.75, is fine, right? And the probability is the area under the curve. But look at what I labeled this axis with. This horizontal axis, the way I've labeled it, is in terms of X bar instead of X. Please make note of that. It's in terms of X bar instead of X. Because I'm calculating the probability that a sample mean would be between certain values. This should be an X bar here instead of an X. All right. And so I'm going to do that right quick because it's going to drive me crazy. Give me 1 second here. So you see my X bar. All right. And so now that I have that, right? So we have our distribution and we know we want to find the area under the curve here between these two values here. And remember, this is a curve that represents the distribution of X bars and not the distribution of X. That is also why I have X bar here instead of X. It's very slight differences. So it may look alike, but that notation is very important. That notation is very important. So if I want to find that probability, I've got to find the area under that shaded area, the area under the curve, which is shaded right there, right? In order for me to do that, I have to convert these values 2.5 and 2.75. We need to convert those to z-scores, all right? We're going to use the same formula. We take the observation, we subtract the mean of that normal distribution, and we divide by that standard deviation here. I think one of the most missed or overlooked things when students are learning this is that they always resort to going back to this standard deviation here. We're trying to find a probability that the sample mean will be between these values. Which is why we're looking at the distribution of the sample mean, right? And it has a mean of this and a different standard deviation, right? Because it's going to be a little thinner. So I'm going to convert this value to a z-score. So I'm going to take this 2.5 here, subtract this mean, which is also 2.5, and I'm going to divide by the standard deviation. I get 0, right? Because 2.5 is the mean, so the z-score is 0. I want to find the z-score for 2.75. I'm going to do the same thing. And when I do that, I get 2.083. And so what I'm going to need to do is go to JASP. These are my z-scores. If you remember, when we want to find the probability of an area between two z-scores, we take the p-norm function of the first value, which will be 2.083, and we subtract from that the p-norm at the second or the smaller p-value. And so I'm going to z-value, I'm sorry. I'm going to do p-norm. 2.083 was my z-value. I'm going to put my mean in there, my standard deviation. And remember, I have lower tail. Lower.tail equals true. So that's going to be the whole area from 2.083 all the way down to negative infinity or to the left tail. That area is too big, so we need to subtract from that the area under the curve for values that are less than my other z-score. I think I said p-value earlier, or z-value, z-score, which was 0. I have the same mean of 0, standard deviation of 1. And I can run this code and I get 0.4813. All right. And so the probability that the researcher will obtain a sample mean between 2.5 and 2.75 is 0.48 approximately. All right. So that's the probability of obtaining a sample. Or I can say that this is the proportion of sample means that I expect to be between 2.5 and 2.75 hours. All right. I want you to notice how this problem here is written. It gives me the mean and the standard deviation of a population distribution, and it tells me what my sample size is. And I'm finding a probability or proportion related to a statistic or the sample mean. All right. I don't want you to confuse that with, and I'm going to go back to one of our earlier examples. An example like this. In this example, we're given some information about a distribution, right? We have a population distribution that's excuse me, that's normally distributed with a mean of 8 and a standard deviation of 1.5. So we're giving a mean and a standard deviation, but notice what we're trying to find here. We want to find the proportion of students that have a running time between 6.05 and 11.15. It's about values of the original variable, not values of the sample mean. That is the key difference of using the sampling distribution stuff or just using the regular old normal distribution. We use the normal distribution. We're finding proportions about values of the random variable, right? Whatever variable in its normal units. Fast forward to what we just talked about in that last example, we're finding the probability or a proportion related to the actual statistic. What's the probability that the sample mean is going to be between certain values? That is the key for when we use sampling distribution stuff or regular normal distribution stuff. I'm going to stop here. There are a lot of practice problems for you to get more experience in doing problems like this. And so you'll definitely do the practice problems. The solutions are also posted. And if you see any issues with the solutions, always feel free to get in contact with me for further assistance. That is it for this module. Do the practice problems, and I think you will be prepared for any other assignments related to the normal distribution, sampling distribution of sample mean, and the central limit theorem.